Hello, welcome to this module of Functional Near Infrared Spectroscopy. I am Dr. Sanjay Kumar Patel, Senior Resident, Department of Physiology, All India Institute of Medical Science, New Delhi. This module comes under the paper 08, that is Medical Physics, which comes under the subject Biophysics. So, welcome to module 11 of paper 08, that is Functional Near Infrared Spectroscopy. In short, we call it FNIRS. Let's talk about the specific learning objectives. At the end of this lecture, students should be able to explain the principles of FNIRS, that is Functional Near Infrared Spectroscopy. At the end of this lecture, the students should be able to describe in brief the apparatus settings for the FNIRS. The students should be able to describe the various techniques of FNIRS, and at the end of this FNIRS lecture, the students should be able to give a brief account the various clinical uses of FNIRS. So, before going into the topic, let's overview the lecture. Under these headings, I will be talking about FNIRS. First, I will be introducing the technique or the functional near infrared spectroscopy. Then I will talk about a brief history of this technique called FNIRS, and then the principles of functional near infrared spectroscopy, under what principles it works, and then the apparatus setting. After that, I will be talking about various FNIRS system types. After that, I will be talking about the certain clinical applications of FNIRS. Then, before summarizing, I will be talking about some future aspects of this very important technique FNIRS, and after that I will be summarizing the lecture. So, first let us introduce the topic, that is FNIRS. What is FNIRS? It is functional near infrared spectroscopy. It is the use of near infrared spectroscopy. Remember, this is not infrared spectroscopy, we call it near infrared spectroscopy, for the purpose of functional neuroimaging. There are various techniques of functional neuroimaging that are available today for imaging of various parts of the body. This FNIRS is one of the most used functional neuroimaging. Brain activity is measured through the hemodynamic responses associated with neuron behavior. So, in brain there are neuronal behavior occurring. Along with these neuronal behaviors, there are hemodynamic responses as per the neuronal behaviors. So, this FNIRS acts as a bridge between the brain and computer, in the simple words we can say. So, near infrared spectroscopy NIRS was originally designed for clinical monitoring of tissue oxygenation. We will talk about in detail in this module how this tissue oxygenation can be recorded using this type of neuroimaging technique or the monitoring technique. Continuing with the introduction, this technique FNIRS has been developing into a useful tool for neuroimaging in the last few decades. This technique does not require strict motion restriction and can be used in daily life. That means the patient or the subject is not mandatory to be in resting position or in sitting or standing. It can be done in any position or even during movement of the body. This technique does not require strict motion restriction and can be used in daily life environment. Functional near infrared spectroscopy, that is in short FNIRS, is an emerging functional neuroimaging technology. It offers a relatively, remember, it is non-invasive. We do not go inside the body, it is non-invasive, and it is pretty safe. It is portable, we can carry it anywhere, in the clinics, in the wards, teaching rooms, and pretty economic. It is low cost method of indirect and direct monitoring of brain activity. So, these 4 or 5 characteristic features are very much important in FNIRS, that is non-invasive, safe, portable and low cost method, and also it takes account of the indirect and direct monitoring. So, before going into any neuroimaging technique, we should know about a brief history, how this technique was evolved in various time periods. So, first talk about the history of FNIRS. Way back in 1977, Jobis reported that the brain tissue transparency to near infrared light allowed a non-invasive and continuous method of tissue oxygen saturation using trans-illumination in neonates. He studied it in neonates. This trans-illumination, in other words it is called forward scattering, was of limited utility in adults. Since he studied in neonates, later on it was found that this has very limited utility in adults because of light attenuation and was quickly replaced by reflectance mode based techniques. So, since it was not very useful in adults, it was quickly replaced by the reflectance mode based techniques. Development of NIRS system proceeded rapidly, and by 1985 the first studies on cerebral oxygenation were conducted by M. Ferrari. So, it was in 1985 that the studies which included the cerebral oxygenation. NIRS techniques were expanded on by the work of Randall, Barber, Britton Chance, Amov Villinger, M. Cope, D.T. Dipley, Enrique Gratton and some other workers. So, first and pretty important topic of this module is the principles of FNIRS. Under what mechanism it works. So, functional optical imaging utilizes the changing optical properties of these tissues by using light in the near infrared. This word will come again and again in this module. The near infrared range means 700 to 900 nanometer to measure physiological changes. The ionic fluxes due to various neuronal behavior in the brain, the ionic fluxes that occur during the neuronal activities also causes change in the magnetic and electrical fields in the brain. This increase in neuronal activity results in increased glucose and oxygen consumption from the local capillary bed. So, whenever there is any neuronal activity, it changes the electrical and magnetic field in the vicinity. Along with it, there is also increased glucose and oxygen consumption from the local capillary bed. A reduction in local glucose and oxygen stimulates the brain to increase the local arteriolar vasodilation. So, it is indirectly the local factors mediated vasodilation. Whenever there is decrease in the local glucose and oxygen, the local factors stimulate this vasodilation, which increase local cerebral blood flow and cerebral blood volume. So, decrease in the blood glucose and oxygen will cause the local vasodilation. This local vasodilation will further increase the cerebral blood flow and subsequently the cerebral blood volume. This is known as neurovascular coupling. So, this neurovascular coupling should be understood properly before going into the mechanism of FNIRS. Continuing with the principle of FNIRS, the increased oxygen transport that is due to the neurovascular coupling to the area typically exceeds the local neuronal rate of oxygen utilization. So, whatever oxygen is being utilized at the tissue, there are more amount of oxygen transport to the particular tissue due to that neurovascular coupling. It results in an overabundance of the cerebral blood oxygenation in the active area. So, we will find more of oxygen in that particular area. The initial increase in neuronal activity is thought to result in a focal increase in deoxygenated hemoglobin in the capillary bed as oxygen is withdrawn from the hemoglobin for use in the metabolic glucose. So, due to this mechanism, there is focal increase in the deoxygenated hemoglobin. Because of this, oxygenated and deoxygenated hemoglobin have characteristic optical properties. If we analyze the oxygenated and deoxygenated hemoglobin, they exhibit different optical properties. So, this difference in optical properties is visible, and this difference is in the near infrared light range. The change in concentration of these molecules during neurovascular coupling can be measured using optical methods. So, neurovascular coupling occurs, there is more of oxygenation, after that there is more of deoxygenation, and both oxygenated and deoxygenated hemoglobin, since they have different optical properties, we use this difference in their optical properties to analyze this blood flow and the neurovascular coupling, and using these optical methods. Continuing with the principles of FNIRS, the most commonly used method of near-infrared spectroscopy measures change in the ratio of oxygenated hemoglobin to blood volume. So, the ratio that is established by oxygenated hemoglobin, that we call oxyhemoglobin, to blood volume, it is the most commonly used method for near-infrared spectroscopy. Most biological tissues are relatively transparent to light in the near-infrared range between 700 to 900 nanometer. So, between this infrared range, that is 700 to 900 millimeter, it is found that most biological tissue are relatively transparent, largely because of water. Because in most of the tissues, water is the main component, main constituent. A major component of most tissues absorb very little energy at this wavelength. This spectral band is often referred to as the optical window. So, this 700 to 900 nanometer is that's why called optical window for the non-invasive assessment of the brain activation. We are continuing with the principles of functional near-infrared spectroscopy. The change in light intensity measured at the surface of the scalp are quantified using a modified Beer-Lambert law. It is a hemodynamic law, the Beer-Lambert law, which is essentially an empirical description of optical attenuation in a high scattering medium. By measuring absorption changes at two or more wavelengths, one of which is more sensitive to oxyhemoglobin and the other to deoxyhemoglobin, changes in the relative concentration of these chromophores can be calculated. Here the chromophores are this oxyhemoglobin and deoxyhemoglobin, since they exhibit two different optical properties and their concentration is measured under this using this modified Beer-Lambert law, and thus FNIRS measures the change in the blood flow according to the amounts of oxyhemoglobin and deoxyhemoglobin. In addition to hemoglobin, other chromatophores including cytochrome, there are some other chromatophores also, which includes cytochrome C oxidase. It can be also assessed using this technique of optical differences. Cytochrome C oxidase, a marker of metabolic demands, holds the potential to provide more direct information about neuronal activity than hemoglobin. But the cytochrome C oxidase is not used that extensively as oxyhemoglobin or deoxyhemoglobin, but it can be used since it is a marker of metabolic demands. So, it has the potential to provide more direct information than hemoglobin about the neuronal activity in the brain or any other tissues. This diagram is all about absorption characteristic of oxyhemoglobin and deoxyhemoglobin and water according to the light wavelengths. In x-axis, we can see the various wavelengths, that is in nanometer, 600 nanometer, 700 nanometer, 800, 900, 1000 and 1100 nanometer. In y-axis, there are absorption factors in reciprocal of the centimeter. So, here we can see the oxyhemoglobin and the deoxyhemoglobin, they have very distinct optical property in the range of 700 to 900 nanometer. Difference in this particular wavelength can be used to assess their amount in this technique of FNIRS. Whereas the water has the peak at the wavelength of around 1000 nanometer. So, there is a difference of both oxyhemoglobin and deoxyhemoglobin than water, and also there is difference amongst them, the oxyhemoglobin and deoxyhemoglobin. Here we can see There is the banana shaped photon path that we will be discussing in the further slides. But to prime all of you, the one is light emission, the one probe is the light emission, another probe is for the light detection. So the light in the range of 700 to 900 millimeter is emitted from one probe and it gets detected by the other probe, and the light inside the brain follows a banana shaped path. The photons travel in the brain tissues in a curved shape. That's why it's called banana shaped path. That's why we assess the change in the blood volume in the brain tissue. Coming to the apparatus setting of this FNIRS, a functional near infrared apparatus is comprised of a light source, as we have seen just now in the diagram, that is coupled to the participant's head via either light emitting diodes or through fiber optical bundles, and with a light detector that receives the light after it has interacted with the tissue. So there are two probes, one is the light emitting diode or the fiber optical bundles, and another one is the light detector that detects the light after the light has interacted with the tissues, and it detects the change in wavelength, and according to the change in wavelength of the emitted light, we detect the oxyhemoglobin or the deoxyhemoglobin that are present in the blood, and after that we can infer the rate of the blood flow or the amount of the blood flow and the volume. As light is scattered after the entering the tissue, a photoreceptor placed 2 to 7 centimeter away from the optode can collect the light after it has passed through the tissue. So distance between the light emitter and the light collector is in the range of 2 to 7 centimeter. When the distance between the source and the photo detector is set at 4 centimeter, the FNIRS signal becomes sensitive to hemodynamic changes within the top 2 to 3 millimeter of the cortex. So at the top 2 to 3 or the superficial 2 to 3 millimeter of the cortex, if there are any hemodynamically changes at that level, it is best detected when the distance between the source and the photo detector is set at a distance of 4 centimeter, and it extends laterally 1 centimeter to either side also, perpendicular to the axis of the source detector spacing. Coming to the various FNIRS system types, we have several FNIRS system type. A wide variety of available FNIR instruments differ with respect to their use of system engineering, with combination between light sources, detectors and instrument electronics that result in balance in the information available for analysis, their safety and cost. So the techniques basically differ in their engineering technique, the system engineerings. There are 4 distinct types of FNIRS implementation have been developed till now. These 4 distinct types are: first is time resolved systems, frequency domain systems, continuous wave spectroscopy systems, and spatially resolved spectroscopy system. So we will talk one by one. First, the time resolved system. A short near infrared pulse is introduced with a pulse length usually on the order of picoseconds. Photon path length may be directly observed by dividing resolve time by the speed of light. Because of the need for high speed detection and high speed emitters, time resolved methods are the most expensive and technically complicated method. Information about hemodynamic changes can be found in attenuation, decay and the time profile of the backscattered signal. So the resolution of this system is time based. In frequency domain systems, NIR, this near infrared laser sources provide an amplitude modulated sinusoid at frequency near 100 MHz. Changes in the backscattered signals amplitude and phase provide a direct measurement of absorption and scattering coefficient of the tissue, thus obviating the need for information about photon path length. So there is the need of this information about the photon path length from the scattering and absorption coefficients. The change in the concentration of hemodynamic parameters are determined. So from this photon path length, this change in concentration of the hemodynamic parameters are calculated. Because of the need for modulated lasers as well as phasic measurements, frequency domain systems are more technically complex than continuous wave system that we talk after this. However, these frequency domain systems are capable of providing absolute concentration of oxyhemoglobin and deoxyhemoglobin. Due to this frequency related domain changes, this oxyhemoglobin and deoxyhemoglobin can be best calculated using this technique. So this is the most accurate technique. Continuous wave FNIR, the functional near spectroscopy, uses light sources which emit light at a constant frequency and amplitude. So here the characteristic feature is the emitting light, and that will be the continuous wave. Changes in light intensity can be related to changes in relative concentration of hemoglobin through the modified Beer-Lambert law that we have talked about. Due to their simplicity and cost effectiveness, these techniques are the most common form of functional FNIRS. Continuing with the continuous wave spectroscopy system, many continuous wave FNIR commercial systems use estimation of photon path length derived from computerized simulation. They use the computer-based simulation models and physical models to provide the absolute quantification of hemoglobin concentration. Simplicity of principle allows continuous wave devices to be rapidly developed for different applications such as neonatal care, patient monitoring system, optical tomography system, and many more. These continuous spectroscopy systems are often wireless. So wireless continuous wave system have been developed in the recent times, which allows monitoring of individual in ambulatory, clinical and sports environment also. This is the last type of the FNIRS system type, that is spatially resolved electroscopy. We have talked about time resolved, we have talked about continuous wave. This is spatially resolved spectroscopy. We have also talked about the frequency resolved. This is spatially resolved. Spatially resolved electroscopy system use localized gradients in light attenuation to determine absolute ratio of oxyhemoglobin and deoxyhemoglobin. So what do they use? They use the localized gradients of light attenuation. By using spatial measurements, these systems do not require knowledge of the photon path length to make this calculation. This photon path length was required in the earlier techniques, but this spatially resolved spectroscopy do not require the knowledge of the photon path length. However, the measured concentration of oxyhemoglobin and deoxyhemoglobin are relative to the unknown coefficient of scattering in the media, because we do not know the photon path length. This technique is most commonly used in cerebral oximetry system that report a tissue oxygenation index, or they report as a tissue saturation index. We will not go into the detail of tissue oxygenation index and tissue saturation index. Just remember, these are the indexes that are calculated from this spatially resolved spectroscopy. Now, after discussing about the apparatus setting, after discussing about the principles and various system types, next come to the clinical applications of this technique, that is functional near infrared spectroscopy. Brain activation studies employing FNIRS have been conducted on visual systems, the somatosensory systems, the auditory systems and the language system, and during some motor task also. So these are certain systems of the, we can say, parts of the central nervous system that are studied using this technique. FNIRS studies have also been used to examine a number of cognitive tasks also. The first clinical application of FNIRS have been in the investigation of fetal, as we have seen in the history, and neonatal and infant cerebral oxygenation and functional activation. So, this is pretty useful studying the oxygenation, the cerebral oxygenation in the fetal and neonatal brain. Continuing with the clinical application, FNIRS studies have revealed developmental alterations in the cerebral hemodynamic responses to auditory and visual stimulation. Again, this is more useful in the fetus and the neonatal brains. FNIRS has also been used to characterize cerebral perfusion as a function of surgical events. So, in certain surgical events also this has been studied. FNIRS has also been used to characterize cerebral perfusion as a function of surgical events such as bypass and reperfusion surgeries, and to measure fetal cerebral oxygen supplies during labor and also post-birth asphyxia. These are certain conditions in which the FNIRS has been useful in studying the brain oxygenation. Talking about some more clinical applications, neurological applications have included an evaluation of this following evaluation, like hemodynamic response during the deep brain stimulation, particularly in the Parkinson's disease patients. So, there is hemodynamic response is studied using deep brain stimulation. Brain activation during induced seizures in patients with intractable epilepsy. So, in intractable epilepsy, what we do is we induce seizures using some agents and we study the brain activation. Also, we evaluate the exploration of the pathophysiology of seizures, in particularly the childhood epilepsy. Examination of Alzheimer's patient during verbal fluency and other cognitive tasks also has been done using this functional near infrared spectroscopy. Continuing with the clinical application, there are some more clinical application. Several types of clinical application that could benefit from unique attributes of FNIRS neuroimaging technology are: some people who may not be able to tolerate the confines of an fMRI, that is functional magnetic resonance imaging magnet. In some people they cannot tolerate the MRI. In those patients, this FNIRS can be pretty useful. So, those patients who are not able to remain sufficiently still, because this FNIRS in moving patients also, or in very active patients also, we can do this study. Example: schizophrenics, autistic children, neonates. These are some of the examples of the patients in which it is very difficult to maintain their still posture. So, in those patients, fMRI is not advisable and FNIRS is pretty useful. Patients who require the long-term monitoring of cerebral oxygenation, like for a very long period of time, it is very difficult to maintain the patient in a still posture. So, in those patients, we use this FNIRS technique. Example: premature and other high-risk infants. Also, this FNIRS could be of benefit in following clinical application. Studies that requires repeated low-cost neuroimaging. Since FNIRS is one of those techniques that is economical, portable, non-invasive, so we can use it in the studies which require number of studies, number of observation, number of calculations. So, repeated and low-cost neuroimaging requiring studies, this can be used. For example, treatment study of the image of the cortex for efficacy of the drugs. Applications where the fMRI system would be too expensive or cumbersome. As we know, fMRI is almost pretty useful technique, but it is very expensive as compared to this FNIRS studies. So, those patients who cannot afford the fMRI, we can use FNIRS for use in the clinical scenario. Application that requires ecological validity, because working at a computer or in an educational setting where ecological validity should be there, we can use this FNIRS. Okay, so we have talked about the principles, the apparatus setting, the system types, and we have seen where we can use the FNIRS. Now, since it is a newer technique as compared to the other imaging techniques, let us talk about some future aspects of this functional near infrared spectroscopy. There are a number of technical issues to be explored and practical difficulties to be solved. NIRS, that is near infrared spectroscopy, is a tool distinct from other neuroimaging techniques for the study of brain functions and for the diagnosis, assessment and treatment of psychoneurological diseases. So, it could be studied in those diseases which has not been explored yet. Thus, a variety of novel application of NIRS such as NIRS based brain computer interface are being tried. This NIRS based brain computer interface is currently the area of research for development of this new functional near infrared spectroscopy techniques. NIRS is considered as a possible alternative to even the electrical signals because it is least harmful for the body. Continuing with the future prospects, conventional NIRS instruments detect signals corresponding to relative low hemodynamic responses. In contrast, a much faster signal occurring over a period of times of milliseconds, tens of milliseconds have been detected by both a frequency domain system and a continuous wave system. In the last few years, the development of the multi-channel NIRS system, which has abandoned handedness, one of the most characteristic feature of NIRS, has been focused on the NIRS field. Also, the miniaturization, the decrease in size of this NIRS of this system has also been tried. Thus, NIRS shows great promise for the providing further insight into brain function as a clinical tool. So, we have talked about the history of the FNIRS, we have talked about the principles of FNIRS system, we have seen the various system types, we have seen the apparatus setting, the clinical uses and then the future aspects. After this, let's summarize the today's module. Functional near infrared spectroscopy FNIRS is used for the purpose of functional neuroimaging to measure brain activity through hemodynamic responses associated with neuronal behavior. Functional optical imaging utilizes the change in the optical properties of the tissues by using light in the near infrared range, that is 700 to 900 nanometer, to measure physiological changes. The most commonly used method of near infrared spectroscopy measures changes in the ratio of oxyhemoglobin to blood volume. A functional near infrared apparatus is comprised of a light source that is coupled to the participant's head via either light emitting diodes or through fiber optical bundles and with a light detector that receives the light after it has interacted with the tissue. There are 4 distinct types of FNIRS implementation have been developed: time-resolved system, frequency domain system, continuous wave spectroscopy systems and specially resolved electroscopy system. Time-resolved and frequency domain systems provide information on shifts in both phase and amplitude of the light and are necessary for more precise quantification of FNIRS signal, whereas continuous wave system apply either continuous or a slow pulsed light to tissue and measures the attenuation of amplitude of the incident light. Brain activation studies employing FNIRS have been conducted on many diseases involving mainly the visual system, the somatosensory system, the auditory system and the language system during the motor tasks. Thank you.